All right, today we are talking about section 10.5, displacement and density. So it says, what happens if you step into a bathtub that is filled to the brim? If you add a scoop of ice cream to a glass filled with root beer? In each case, you'll have a mess. The volume of the liquid that overflows in each case equals the volume of the solid below the liquid level. Let me read that again. That's an important sentence. The volume of the liquid that overflows in each case equals the volume of the solid below the liquid level. This volume is called an object's displacement. So far in this chapter, we have calculated volumes of polyhedrons based on a volume formula that says find the area of the base and multiply by the height, right? And every shape that we've calculated the volume of, we've been able to apply that volume formula to. However, there certainly are objects out there that are not polyhedrons, right? You could get some abnormal, irregular solid that you want to calculate the volume of. This is where displacement becomes valuable. It says, Mary Jo wants to find the volume of an irregularly shaped rock. She puts some water into a rectangular prism with a base that measures 10 centimeters by 15 centimeters. When the rock is put into the container, Mary Jo notices that the water level rises 2 centimeters because the rock displaces its volume of water. This new slice of water has a volume of 2 times 10 times 15, or 300 centimeters cubed. So the volume of the rock is 300 centimeters cubed. So let's take a look at these two diagrams. On the left, the before picture is just the rectangular prism with the amount of water that Mary Jo put into it, right? Now she drops the rock in, and after the rock has sunk to the bottom, the whole rock is below the level of the water, so it displaces its volume. So you can see they drew in a dotted line here of the original water level, right there. And the rock has displaced the amount of water equal to its own volume, and that water level has risen 2 centimeters, right? They tell us 2 centimeters. So what Mary Jo knows is if she can calculate the volume of water that has been displaced, it will be the volume of the rock. So length times width times height, 2 times 10 times 15, or 300 centimeters cubed. All right, so here's the process that you would go through to find the volume of some irregularly shaped object. Density is the mass of matter in a given volume. You can find the mass of any object by weighing it. You calculate density by dividing the mass by the volume. So this may be a formula that you've seen in chemistry or some other science class, right? Density equals mass divided by volume. So here's an example we're going to apply our displacement and density to. It says a clump of metal with mass 351.4 grams is dropped into a cylindrical container, causing the water level to rise 1.1 centimeters. The radius of the base of the container is 3.0 centimeters. What is the density of the metal? Given the table and assuming the metal is pure, what is the metal? We need to find the volume of the metal by finding the volume of the displaced water. So we have a cylindrical container, and we know that the base of the cylinder is a circle, so pi r squared times the height, but only the height of the water level, right? Not the height of the whole cylinder. So volume would be pi times the radius they gave us was 3, times the height of the water level. They said it rose 1.1 centimeters. So that's going to give us the volume of the metal. Put that into the calculator. 31.1 centimeters cubed. So now to find the density, we know density equals mass divided by volume. Well, they told us the mass was 351.4 grams. And the volume we just calculated, 31.1. So we divide those. 11.3 grams per centimeter cubed. So there's the density of our metal. Now we just look at the table, right? And we look and we see lead, 11.3 grams per centimeter cubed. All right, here's a fun or funny history connection. It says, Archimedes solved the problem of how to tell whether a crown was made of genuine gold by using displacement to calculate its density. Legend has it that the insight came to him while he was bathing. Thrilled by his discovery, Archimedes ran through the streets shouting, Eureka! Greek for I have found it, wearing just what he'd been wearing in the bathtub.